Hello everyone. In this video, I will be discussing the environmental behavior of persistent organic pollutants, or POPs. The video will be separated in several sections, and each section will deal with a different learning outcome. In this first video, I'm going to discuss the key characteristics and key environmental impacts of types of POPs, and I will be specifically focusing on chlorinated compounds. This is the bibliography I've used for the session. You have access to Harrison's chapter through the Novel database, and there is a link on Blackboard. I've also used BART environmental chemistry, a bit on the section of pesticides, and also chapter 8, other organic pollutants. You do not have access to that on the model Blackboard. This is a paper book. You will have to get it from the library. And finally, this resource from the University of Missouri, Pesticides and Environment, which is a short 6-page PDF that gives a brief overview of the environmental fate of a chemical, in this case a pesticide. So what are persistent organic pollutants? Well, they are chemicals, they have a definition. They are a set of chemicals that have the potential for long-range transboundary air transport. They also, to be a POP, need to have to show toxicity to either humans or the environment, or both. And they need to be persistent. And there are some specific definitions of how persistent they need to be. So evidence that chemicals half-life in water is more than 2 months, or that the half-life in sediments is more than 6 months. Alternatively, they have to show evidence that the substance is persistent, even if not for those lengths of time, and show bioaccumulation. The evidence is if the bioconcentration factor or bioaccumulation factor is higher than 5,000, and I will be discussing what BCF and BAF are later in the video, or the log of KOW, log of the partition coefficient octanol water larger than 5. And again, I will be discussing partition coefficients octanol water later. Or they don't have a huge potential for bioaccumulate, but their toxicity levels is serious enough that grants it making them a concern. This is a set of chemicals that is regulated by the Stockholm Convention on Persistent Organic Pollutants. The convention started in 2001, and it was signed, it came into force in 2004. And initially it covered 12 POPs, to which a few others have been added later on. So these are some of the key pollutants that make it into a persistent organic pollutant, and which were in the original list of the 12 pollutants that were mentioned in the Stockholm Convention. The first type I'm going to cover is PCDDs and PCDFs. Those are polychlorinated dibenzodioxins and polychlorinated dibenzofurans. They are not produced on purpose intentionally, but they are sometimes industrial byproducts of other reactions. And you can have here the example of how a dioxin looks like and how a PCDF looks like. This center ring here is the dioxin ring, and this one is a furan. And here I've got an example of a particular one. They have different toxicity depending on the number of chlorine atoms in the structure. And as a general rule, the more chlorine atoms, the more toxic they are. And that is because, and the more persistent they tend to be. And that is because both the structure, the general structure with these two benzene rings is difficult to break down in nature, and also chlorine atoms are also difficult to break down, so that both the PCDDs and the PCDFs and the breakdown products are very persistent and stay for months in the environment, and are not broken down by environmental systems. Another example of persistent organic pollutants is PCBs, and PCB stands for polychlorinated biphenyls, and these are commercial products. For example, they are used in transformers, and this is the general structure of a PCB. The two benzene rings are biphenyl, the biphenyl compound, and they have several chlorine atoms. As in the previous case, in general, the more chlorine atoms, the more the environmental concern of the PCB. The next type of POPs I'm going to mention are called PAHs, polyaromatic hydrocarbons. Again, they are not intentionally produced, but they come out of combustion of internal combustion engines or the burning of fossil fuels, etc. There are quite a few of them, and they all have this structure. Can you see all these benzene rings fused in different shapes? And again, they are difficult to break down in nature because of the stability of those fused benzene rings. Makes them quite difficult for environmental systems, for ecosystems to break down, to metabolize or break down in the environment. There are a category called OCPs, organochlorine pesticides. And these ones are a mixed bag of pesticides which contain quite a few chlorine atoms, but that's the only thing they have in common in the structure. I've given here the example of the two most famous ones, both currently banned. One is DDT and the other one is aldrin. And as you can see, the structure itself is not, they don't have that many things in common except the presence of quite a few chlorine atoms. And again, they are very difficult to break down, and that presence of chlorine atoms makes them particularly difficult for the environment to deal with, to be able to absorb and break down into harmless chemicals. These are the 12 initial persistent organic pollutants under the Stockholm Convention, and it covers pesticides, it covers some industrial chemicals, for example PCBs, and it also covers some byproducts, so no intentionally produced but byproducts of industrial reactions, for example some PCBs and PCDDs and PCDFs. Initially, the convention had 12 chemicals, and that was increased a few years later to up to 16. And at the moment of recording this video, there are another 3 or 4 currently under consideration to be included as part of the convention. And the convention regulates the levels that are allowed in the atmosphere, the levels that are allowed in the environment, and it bans some of them. For example, DDT or aldrin are banned pesticides, and DDT can be used only in very, very specific conditions. Adverse effects. Their effects vary depending on the structure, and they are not all as dangerous as others. In general, they are suspected carcinogenic, so they are carcinogenics. Some of them affect immune responses. They can be teratogenic, neurotoxics. They have effects on the reproductive system. Organochlorine pesticides, for example, DDT is very famous for the effect in reduced fertility or affecting the eggshells, the thinning of the eggshells. Some of them have direct toxic effects, although in some cases there is a lack of data of their direct effect in humans. But in general, it is the effects in the reproductive system, the toxicity for both humans and or the environment, and their persistence that makes them an environmental issue of concern. How are they monitored? Well, you can find them, as we will discuss later, in air, in soil and water. In soil, they tend to be trapped on the top 5-10 centimeters of soil. You also need to study air samples, since they are volatile, and we discuss volatility later on. And when they are in air, sometimes there's the difficulty of they are mixed with dust emissions, for example, from cars, car soot and particulate matter, and water samples. In general, they are highly hydrophobic. They don't mix well with water, and they tend to accumulate in fatty tissues. And in general, when you find them in water, they tend to be associated, adsorbed in the particle matter in the water rather than dissolving water themselves. They can be analyzed by several techniques, and some of the typical ones are GCMS, which stands for gas chromatography mass spectrometry, and HPLC, high performance liquid chromatography. And we will have a whole week dedicated to these analytical techniques. And I will also introduce some more information about how to monitor and analyze persistent organic pollutants using these techniques. So what happens when they are released in the environment? Well, one thing that you need to take into account is their ability to volatilize, to go from a solid or liquid form to a gas form. And once they volatilize, they can move in air, and they can move across quite long distances, and that's why they're a transboundary air pollution problem. How easy they volatilize depends on their vapor pressure, on their structure. In general, the higher the vapor pressure, the more volatile it is, the easier it is to become gas, to get into a gas form. Their volatility is also influenced by the temperature and the humidity of the air and the air movement. For example, winds helps them move across long distances. High temperature makes them more volatile, and low relative humidity, dry air, again makes them more volatile. If the air is very saturated with water, it will be difficult for the pollutant to get into gas form. It also influences things like the soil. If the pollutant is absorbing the soil, or for example, if it's a pesticide and is found in the soil, soil conditions like the texture of the soil, the organic matter content, and the moisture content influence how volatile that chemical, for example, a pesticide, that persistent organic pollutant, how volatile it is. So, for example, a high organic matter content tends to keep the pulp trapped in the soil. And the same with the texture, very fine texture, high surface areas tend to keep the chemical in the soil, and thus prevents it from volatilizing. What's the problem with volatility with persistent organic pollutants? Well, once they get into the air, they can move long distances. If you're looking at a pesticide, a very volatile pesticide means that the vapors of the pesticide can injure non-target plants, and you have a reduced control of the target pest, since the pesticide literally will fly away from the area where you have sprayed it. They also have the ability to move through the soil, and we call that leaching. And how easy a compound will leach, how easy it will move across the soil, and it will dissolve in water and will move through the soil, depends on that chemical's physical and chemical properties. When persistent organic pollutant is strongly adsorbed on the soil, it is less likely that it will leach. And a compound that has a low solubility in water will not move through the soil, will not dissolve in water so easily, and they will not move away from the soil. And the opposite is also true. If the compound is more soluble in water, it is more likely to leave the soil and get into the water. And again, things like the texture of the soil, fine soils tend to avoid the chemical leaching, tend to keep the chemical, the persistent organic pollutant trapped in the soil. The organic matter content, the higher the organic matter content, the easier will be to for the persistent organic pollutant to stay in the soil. Or permeability will affect the ability of a persistent organic pollutant to leach. And this is all for this video. I hope it was useful. And again, if you have any questions, please contact me or post in the chat.